Good morning, children. Today we will study about the second application of Gauss law, that is the electric field due to a uniformly charged infinite plane sheet. Let's take an infinite plane sheet whose a part of this plane sheet is shown here. Let's take this as the plane sheet which is uniformly charged. So let's say, for example, this is positively charged uniformly all over and its surface charge density is sigma. Sigma is the uniform surface charge density for this sheet. We have to find the expression for the electric field due to an infinite uniformly charged plane sheet. We are using Gauss law over here. So for Gauss law, we know that we need to select a Gaussian surface. So that Gaussian surface must be symmetrical in order to make the calculations easy. So let's take a Gaussian surface which is a cylindrical Gaussian surface such that this sheet is at the center along its length. Now this is the Gaussian surface, for example. I am taking this sheet. So this is an imaginary Gaussian surface. I am showing here with the help of this cylinder, but this is actually imaginary. So imaginary means we can consider it to be passing through this sheet. So this is the case where we can consider that this is the sheet and the Gaussian surface is cylindrical, where half of the part is here, half of the part is here. So that means if we draw this Gaussian surface which is cylindrical in this diagram, we can consider this cylindrical surface to pass through this and this part which is coming out from this is distant r from the sheet on this side, and similarly this part is also distant r from the sheet. Let's take that this part of the cylinder has an area A. This part also has an area A. Now we know that if this is the sheet, then electric field due to this sheet, because this is positively charged, will be outwards everywhere. Right? Here also it will be outward this way. So we can say that whether we consider a point here, whether we consider a point here, or whether we consider a point here, at all these points the electric field direction on the right side will be this way. Similarly, if we consider any point on the left side, the electric field direction will be this way, electric field direction will be this way, and here also this is the direction of electric field. Right? For deriving the formula for the electric field due to this sheet, we are using Gauss law. So by Gauss law, we have first expression which is phi total is equal to Q upon epsilon naught, where this is charge and closed. And we have another formula for flux, that is flux is equal to E dot ds integral, surface integral. So we have to find out the flux through this total Gaussian surface that will be equal to the flux due to this surface by Gauss theorem. So for this, how many surfaces do we have here? First is this surface, second is this surface, and the third is the curved surface. So you can say that here flux total is equal to flux due to first surface, flux due to second surface plus flux due to the third surface. We can write down the formula here that this is E ds cos of theta, where theta is the angle between E and the surface area vector. Now look at this face of this cylinder. The area vector will have this direction. So what will be the theta between area vector and electric field? 0 degree. Similarly, electric field vector is this way and area vector is always normally outwards. So what will be the direction of area vector? This one. So here also theta is 0 degree. Now let's consider the curved surface. If we consider a small surface area ds3 over here. So what will be the direction of ds3? This one. Because if we have this cylinder, then at this face the surface area vector will be this. But on curved surface, here it will be this way, normally outward. Here it will be this way. Here it will be this way downwards. Here it will be this way. And at every point, the area vector will be normal to the surface. So we are considering this point here. So this is the area vector and this is the electric field vector. So what is the angle between this and this? This angle is 90 degrees. So now you can replace this by formula and put the values of angles. So phi total is equal to first surface is this one. So this is E dot A, right? Plus second surface. This is E dot A. Third surface, we need to write E dot ds3. But this is a small surface area. Here this is complete surface area. So we need to integrate this because this will be the flux due to the small surface area and that will be d phi. So we need to integrate this. This makes it EA, look at the angle, cos of 0 degree plus for second surface check, theta is 0. So this is again EA cos 0 plus, what is this? E ds3 cos of how much? This is 90 degree. So cos of 90 degree and integrate. Cos 0 is 1. So this is EA. This is also EA plus, but this is cos 90. So this makes it 0. So this phi total is 2 times of EA and this is phi total. Let's consider this as the first equation, this as the second equation. Let's equate these two. Now first is equal to 2. Equation first is equal to 2. So you can say that 2 times of EA is equal to Q upon epsilon naught. This gives us E is equal to Q upon 2 epsilon naught A. Now if we look at this, we know that Q upon A is surface charge density sigma for this sheet. So this makes it sigma upon 2 epsilon naught. This is the formula for the electric field due to an an infinite sheet which is uniformly charged. And if you want to write down this in vector form, you can write down sigma upon 2 epsilon naught r cap, where r cap is a unit vector normally outward to the sheet. Normally outward to the sheet. Now, if I want to draw the graph between electric field and the distance, so I can place this electric field here and distance vector here, and we know that in this expression r is not there, distance is not there, so you can say that E does not depend on r. So you can say that ER graph is this one, where this graph is parallel to our axis. That means E is independent. I hope you understood. Now here I want to mention one more thing. In some books, the Gaussian surface chosen is not cylindrical but rectangular parallelepiped. So I need to explain that whatever be the shape of Gaussian surface, it will not make any impact on the result. Why so? Suppose I am taking this rectangular parallelepiped and this again I am placing such that half of the part is here, half of the part is here. Now let's check the area vectors. For this rectangular parallelepiped, for this space, the area vector is this way. So angle between area and electric field is same, 0 degree. For this space, the angle between electric field and area vector is same. Let's check this space. Area vector is this, electric field is this. How much is the angle? 90 degree. If we check this space, this is the area vector, this is the electric field vector, again 90 degree. Check this space. This is the area vector, this is the electric field, again 90 degree. And for this space also, this is the surface area vector, this is the electric field vector, so angle is 90 degree. So there is no contribution to flux through these side faces. Only contribution is through this face and this face. As in case of cylinder, the contribution to electric flux by this curved surface is 0, and only this and this face contribute to electric flux. That's why choice of the Gaussian surface does not affect our result. Thank you. That's all for now.